Hola, hi, this is Al, your probability and statistics instructor. Let's get to work. In this video, I will present you a theorem that, in combination with MGFs, will help us identify the distribution of a transformation of a random variable. Then, what we're going to be doing is applying that theorem to a particular case. Okay? Well, let's begin. So this is the example I would like to discuss. Okay? So as you can see, we have a transformation. We have an original random variable, y, that is normally distributed with mean mu, a Greek m, and variance sigma square, a Greek s squared. Okay, so but then we based on y, we change it, we transform it a little bit, right? We shift it. Okay, so we remove the mean. So we want to see what happens when we do that transformation. Okay, so first what we would like to do is finding the moment generating function of that transformation, and then using that MGF to find the expected value and the variance of that transformation. Okay? Now, let me go to our lecture notes. That's the theorem that we want to apply. So we know that the definition of the MGF of a random variable y is the expected value of e to the t times y power. Okay, just like that. Now, in this case, we have a transformation, a generic transformation. We're calling it g of y. Okay, so using, I think it's theorem 4.4, we have the expected value of a function. We know that all we have to do is slightly modify the definition of expected value, of plain expected value of y, and then it's just, in the case of a continuous random variable, the integral from negative infinity to infinity of your transformation times the PDF. Okay? So just take the integral, and instead of using y here as you would for the plain expected value of y, you use the function that defines your transformation here. Okay? Okay. So we are slightly modifying the, if you will, the definition of moment generating function. Okay? It's the moment generating function of a transformation. Okay? Okay. So now let's go back to our problem. Solution. First, just to be friendlier, to make it clearer, right? Let me define a new random variable w, which is going to be y minus mu. Okay. So now, by definition, if I want the moment generating function of the random variable w, just by definition, it would be expected value of e to the power tw. Right? Easy. Straightforward, right? But now let's substitute what w stands for. So w is y minus mu, right? So we have the expected value of t times y minus mu. right? Okay, now let me do a little bit of algebra here. We could re-express this as follows. This would be the expected value of t times y times e to the power minus mu times t. Agreed? Right? Same thing. Okay. Now let's just write this down. Okay? This would be, you know, the integral from negative infinity to infinity of that's our transformation, times PDF of y. Agreed? Right? Expected value of that transformation is just that transformation times the PDF. Okay? Now, note that we are integrating with respect to y, so e to the negative mu t is just a constant with respect to y. So by the linearity of integrals, we get to factor that out. We do that next. There. Okay? But now, take a look at this expression. It's the integral from negative infinity to infinity of e to the power ty times the PDF. That's just the expected value of e to the power ty, right? So let me write that down. This is the expected value of e ty. But that is just by definition the MGF of y. You guys agree? So let me write that down. This is just the MGF and that's just by definition, right? Okay, so we're almost there. In another video, I showed you that your textbook, I think again it's page 837, has two beautiful tables with probability mass functions when we're referring to discrete distributions, and along with means, variances, and MGFs of famous probability distributions. And we have on the next page something very similar for famous continuous distributions. So the MGF of a normal looks like this: e to the power mu times t plus t squared times sigma squared divided by 2. Okay, so we know, right, let me go back to what we have here. We know that the original random variable y is a normal with mean mu and variance sigma squared, which means that using our table, this is the MGF of y. Okay, so let's use our table from our textbook and save some time. So this is e to the power minus mu t times e, we said, right, mu t plus, oh, I want that to be in the exponent, so we have a fraction here, it's going to be t squared times sigma squared divided by 2. Okay. Now let's do a little bit of algebra here. Let me break down this exponential into 2. Okay, so that would be the same as this, the product of 2 exponentials, right? I want this. That's what I want. Okay. You guys agree that the product between these 2 exponentials is the same as this one here? But now the product between these two, right, the sum of their exponents, that's going to be 0, right? E to the 0 power, that's just a 1, so the only term that survives is this guy here. Okay, and that happens to be the MGF of our transformation of our new random variable W, right, where W is y minus mu. That's the transformation that we wanted. Now I want you to take a good look at it. E to the t squared times sigma squared divided by 2. Let's go back to our table here. Then you go, this is the MGF for a normal with a generic mean mu and a generic variance sigma squared. If mu were 0, this disappears, and then you end up with only e to the power t squared times sigma squared divided by 2, right? Which means that the MGF we just found corresponds to the MGF of a normal with mean 0 and variance sigma squared, right? So let's write that down. So this expression corresponds to the MGF of a random variable with a normal distribution with parameters or with mean 0 and variance sigma squared. Something else, we know that MGFs are unique, so that implies that W must be normally distributed with mean 0 and variance sigma squared. So let's just point that out here. Come on, because MGFs are unique, W must be normally distributed with mean 0 and variance sigma squared. So what I want you to remember from this example, right, is that this is another important application of MGFs. That if you compute the MGF of a random variable, or a transformation of a random variable for that matter, and you end up with an expression, an MGF that you are able to recognize, that means that your transformed random variable has that distribution. Make sense? So like in this case, well, the MGF of this transformation, g of y, or of w, right, happens to be the MGF of another normal. So that means that w has a normal distribution with the parameters dictated by the expression you ended up with in your MGF. Make sense? Okay, now for part B, I'm just going to remind you how you could use the MGF to find those moments, the expected value and the variance. By the way, in this case, given what we did, given our observations in part A, we already know that the mean is going to be 0, and we already know that the variance is going to be sigma squared, right? So you could just double check by doing the following, right? For part B, just recall that if you take the first derivative of the MGF with respect to t and evaluate it at 0, then you end up with the expected value, right? So let me just remind you of that. So the expected value of W, that's what we called it, right, is going to be just take your MGF and take the derivative of your MGF with respect to t, evaluate it at 0, and you'll be fine. Okay, let me do it like this. There. So W, we have a prime here, and we have we want to evaluate that derivative at 0. And here, let me remind you, derive with respect to t, okay, or differentiate with respect to t. Take derivative with respect to t. Okay. Now for the other one, the expected value of W squared you can find that easily, right, using your MGF, but now instead of taking the first derivative, you have to take the second derivative. Again, remember, with respect to t, and then you evaluate at 0, right? Okay, and finally, remember that there's an alternative way of finding the variance of a random variable, right? Not just the definition. We could find it in terms of expected values of expected values like this, right? Remember, we talked about that a while ago. Okay? So again, in this case, we already know what the answer must be. We would be just double checking using these properties of MGFs. That first derivative with respect to t of the MGF evaluated at 0 gives you the first moment with respect to the origin, which happens to be the expected value. And then if you take the second derivative with respect to t and evaluate at 0, then you end up with the second moment with respect to the origin, the expected value of W squared. And combining these two expected values, you can easily find the variance. Okay? So in summary, what I want you to remember about what we did here together in this video is that that's why MGFs are very useful, because we can use them to find the distribution of random variables, and of course, as the name implies, MGFs can be used to find moments with respect to the origin of random variables, like expected value, right? And then we can also use it to find the variance, not directly, but in a very straightforward way. Okay, so that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.